So hi, as you can see I'm in the lab today and I'm going to do a project. It's about time, I think, for another small project. And this one is actually a current probe and I'm going to be using it on my oscilloscope mainly, I think, although there's no reason that it can't plug into something like this multimeter just here or here. And I guess one thing that a lot of people are asking is, you know, I've got stacks of multimeters, why do I really need a current probe when the multimeters can measure current? So we'll go across, have a look on the computer at a few little details about measuring current, burden voltage, and then we'll come back and actually get on with some prototyping. I'm going to do this video in two parts. So part one, try it out, prototype it, get it generally working. Part two, build the actual set of prototypes. And I'm going to be building about 10 of these probes because I want to probe multiple things simultaneously. That occur. So our problem is that we have something supplying current, something sinking current. We've got a wire in the middle, or PCB track, or whatever it might be. This could be a power supply, it could just be a transistor supplying another transistor, for example. It could be anything. We've just got something we want to measure the current. And our problem is, how do we measure the current? So we can't just connect one wire. So generally speaking, we'll take a multimeter, we'll cut the wire and stick the meter in the middle of it. Now I say cut the wire, we might be able to measure across the switch, there might be some convenient fuse or something, but irrespective, we need to invade that wire with the multimeter. Now multimeter isn't always good enough, sometimes we need a scope. So we need some sort of probe for the scope that will can be injected into this wire, and then we can measure it on the scope. So what is that probe? Well, the simplest thing is to do the same as the multimeter, which is to put a resistor in it, which is exactly what a multimeter does. So a multimeter will put a resistor into that wire inside its own box, of course, and measure the voltage across it. From Ohm's law, we know that current is the voltage divided by the resistance. So for example, if it puts in a 1 ohm resistor, then we know that it will produce 1 volt for every amp that flows through the resistor. So simple as that. And of course, if we want to use an oscilloscope, we can actually physically put a resistor in our circuit and then connect up the two sides to the meter, to the scope rather. So what is the resistance it puts? Now, in many cases, so for example on this key site, you can look on the data sheet and it will tell you what resistor it uses for each of its different ranges. I set this one onto amps, and I'm going to actually zero out the resistance on here, and I'm just going to stick this in its amp measurement. And there we go. So 0.06, so 0.05, 0.06 ohms is what it's using in its current measurement just there. Now there's thermal drift on there, so it's a bit difficult to measure. I need a four-way measurement for that, but let's switch it into milliamps. Now this is auto ranging, so it's a little bit awkward, but we'll do our best and see what we've got there. So there you go. We've got about 2 ohms resistance in the milliamp range. Of course, putting a resistor in this line is going to actually alter the behavior of the circuit, and in some cases it could alter it absolutely drastically. If we're looking at events relating to circuit failure, for example, which we think might be related to too much current or too little voltage or too little or that the supply isn't doing what it's supposed to be doing, then putting that resistor in there could be the last thing that we really want to do. Now the voltage across here is generally called the burden voltage because it's literally that, it's a burden. The aim is of course to minimize that. So one way of doing that is to reduce the size of the resistor. So instead of 1 ohm, we'll put in, let's say, 10 milliohms, and then we'd put a times 100 amplifier onto the output. And you can buy current sense amplifiers specifically designed for that. One tool which is quite useful, I do have some in my lab, are the micro current golds from EEV blog, and they do this, exactly this. They put a small resistor in, smaller than usual, and they multiply it up. And you can get some meters that are specifically designed to have a low burden voltage for measuring current. But anyway, irrespective, you're going to kind of end up with some sort of burden. Now, often it's good enough, and it's one of the simplest ways of doing things, and it's very reliable, and all that sort of stuff. However, that's not what we're going to build. We are going to build a version which is mainly aimed at dealing with a scope. And the reason we want to do a scope is because if, for example, there are multiple stages, let's say this is a digital circuit over here on the sink, and it's going through stages and then suddenly it's failing and things like that, we might want to look specifically at the current across that failure point. So for that we need a scope, we need to trigger on increasing current, that sort of stuff. We might want to look at actual AC current in power supplies, that sort of stuff. So so we need to have timing information as well as just current. Now a complication is that we want to measure DC current as well as AC current, of course. Now, one way of doing this is to use the fact that the current through a wire creates a magnetic field, and we can sense that field using a Hall effect sensor. And you can get linear Hall effect sensors, which is very helpful. So we don't have to do loads of complicated maths and functions in our circuit. We can just kind of read the value and scale it. So the Hall effect sensor that I'm looking at, I'll put the part number on the screen, has 0.2 to 1.8 volts is its effective output. So at no magnetism it will produce 1 volt. So apparently I'm drawing about 2 milliamps, and there's my 1.0 volts roundabout. Tiny little bit of offset on it, but nothing much. See if I can find a magnet. Yeah, there's some magnets. So let's just bring him closer. There we go. Yeah, we can see the effect of the magnetism. So if I put him on this way, then yeah, I'm pretty much topping out now at nearly 2 volts. Turn it the other way around, and I should go negative, I hope. There we go, heading down towards 0. Seems like it will actually go further than the range specified, which is between 0.2 and 1.8. So that's great. So our amplifier needs first of all to remove that 1 volt offset so that we get a plus minus voltage on the output. So now it's going from minus 0.8 volts to plus 0.8 volts, and we can see that that's quite a small range. Now the magnetism produced by the wire is really tiny. So that's off, that's on. Okay, off, 10039, on 10033. Let's move this to a slightly different location. Got slightly more sensitivity there because of the way that it surrounds the thing. We actually need the field to go right through the center. So we need to amplify that up, and that's fine. And then we put that on a scope or into a meter or whatever. So that's the problem solved, yeah? No, because we've still got signal to noise ratio. Because the change on this sensor is so small, it might only be like 1 milliamp per amp, 1 millivolt per amp or something like that. Then in actual fact, things like environmental noise, noise from the resistors, the thermal noise from the resistors, all that sort of stuff, is actually potentially going to swamp that. We're going to lose sensitivity because we're just down in the noise floor of our circuit. So there's various things we can do. We can choose our amplifier carefully. We can put careful thought into resistors, etc., etc. But the single most effective thing we can do in all circuits, not just this one, is to ensure that we have greatest efficiency in the collection of the signal of interest. The signal of interest is the magnetic field coming off this wire. We can concentrate it, not magnify it, but concentrate it and make that flow more effectively through our sensor if we put a ferrite ring around the actual wire. So that's what we're showing up on the right hand side here. We're showing the wire passing through a ferrite ring. Now we get a circular type magnetic field around this, which corresponds very nicely with the ring. So the ring concentrates the magnetic field round, and from the full 360 degrees of this wire, not just the place where the sensor is, which might be just a couple of degrees, and takes all of that magnetism and concentrates it, and it passes through the sensor in this gap. So the sensor is both screened from outside world interference and simultaneously receiving a more concentrated version of the magnetism that it's trying to detect. So overall the signal to noise ratio improves dramatically. So I've got a couple of ferrites here, one of which I've split, which is this yellow one, and I'm going to try them out on the sensor. And we've got the big cable filter here, and I've just used a Dremel to make a little indent for the sensor to fit into, and I'll just have to tape it round or something like that. So unsure which one will work best, but anyway, I will try both of them out. So for those interested, here are the details of the small yellow toroid that I cut in half. Okay, and I'm literally super gluing this to the toroid. So the sensor's super glued to the toroid. The sensor is 2.3 millimeters thick. That's all. Hopefully this will hold on. Let's take on cable. Take the other half of this. We've got our split core clamped together. We've got our sensor in the middle. We've got our cable running through, and we've got our voltmeter on screen, I think. It should be close to 1 volt. Yeah, so not bad, 1.026, and that's with no current at all. And we need to turn on our current source. So now we've got 100 milliamps flowing. Okay, punching up to 3 amps. So we are looking at about 7 millivolts per 3 amps. So we've about doubled the sensitivity compared to it without a toroid, but it's still pretty low. So I'm going to bring up this toroid now and give that a go instead. I might just need to cut away the plastic a little bit so the sensor will fit better. Okay, so a different sensor just popped inside in that big toroid, all taped up to hold it closed. And this is our no magnetism value, 10084. And we'll start off just putting 100 milliamps through, and yeah, we're already sensing better. Look at that, 100.74. So that's a millivolt for 100 milliamps. So that is already considerably more sensitive. So I'm just winding this up now to about 1 amp, and that's 30 millivolts per amp. So that's a significant improvement over what we had before. So here's my ultra high precision diagram. So I'm thinking something along these lines. It's about 3 inches long in total and about 3/4 of an inch wide. The hole is pretty small, about 4 millimeters, something like that. The reason it's got a lump on the end is because I want to be able to plug in a power supply. I don't mind putting a coax cable on for the scope and having that permanently soldered in, but I'd like to be able to switch the power supply. And there's some specs down the right hand side, which is what I'm aiming at. Okay, let's make a start by just looking at the supply part. So we need a bipolar supply because we want plus and minus swing on our output, and we're going to take 12 to sort of 24 volts. 9 to 30 is the range that the circuit will work out comfortably, and we're using this op amp here as a buffer on a voltage divider. So literally we take, let's say, our 12 volts, we divide it in 2 on that little pair of resistors, and then we use the op amp as a voltage follower to buffer the current, and that gives us 10 milliamps or something like that, and that just stops the 0 volts moving around within the range of the voltages. Looking to the sensor then, it goes through a 2-stage amplifier using a TL072 op amp. The 072 is pretty low noise, it's got good input impedance, it's easy to use, good voltage range. My PCB manufacturer can supply them by the million, and yeah, it's pretty straightforward. And we've got this configured as a inverting amplifier, 2 of them in a row to put the phase back again. And starting at the left hand side, we've got the sensor. This is coming through a 10k resistor, and that's so that we limit the amount of current it is sourcing, because it can only source 300 microamps, and the 10k essentially will bring that down to 100 to 200. So the 10k is running into a virtual ground, but of course actually that's offset above ground. So at 2 volts I would expect about 100 microamps to be flowing through that resistor, which is absolutely fine in terms of the sensor. So the first op amp has only a little bit of gain. Its main job is to offset the input voltage. So we've got a 3.3 volt Zener here, and that's going across, and we're using a trimmer just to pick off the voltage that we need. I'm not entirely sure about that bit of circuit. It might not be that thermally stable, but we'll see how it goes. That goes in the positive, and so normally that's connected to ground, but in this case we're offsetting it slightly to create our offset voltage. I suppose the other thing of note here is that the resistors in the chain are actually a little bit low. There's 1k there, for example. You normally have a higher resistor than that, and we've got a resistor here which is the feedback resistor. This second part of the circuit is giving a times 15, so that will be trimmed. Yep, there we go. So so times 15, and we've got times about 3 on the front, and based on our experiments you'll realise that isn't enough amplification, but I'm going to use a different sensor on the front. So it's actually the same sensor, it's just a different range. They do it in various sensitivities. So I'm using a CA range, and I will use a EA range sensor for this. Okay, the last thing I think to talk about is across the top I've got various capacitors. These are all optional, and they're there just in case we need to do any shaping of frequency response. And the reason is that actually this is a very generic circuit that isn't just for this purpose. I could use it for lots of other things. So we'll have them make up some spare boards and a stencil. Okay, here we are with the breadboard. So we've got our sensor over here, and the amplifier is here in the middle, and on the left hand side we've got our power supply. So we've got our plus minus coming in. I've got that set to 12 volts because I'm expecting to use a 12 volt plug pack. Here's the LM358. Here's the trimmer that trims the offset voltage. There's the Zener diode floating around in midair. No thermal, no thermal thought given to that at all. And these are not the right size trimmers. They're bigger than they should be, so they will have more thermal drift, etc., etc. So I'm not going to worry too much about that until I actually get the final prototype. And then we come through to this guy here, which is the amplifier, and here's our trimmer for the amplification. Okay, so first job, let's just try and trim out this to 0 with no current in there. Had to be said, that is a horribly touchy adjustment, and it's drifting thermally hugely. It's quite cold in here, so it will be heating up quite a lot. Anyway, I think the problem is that there we go, that my ferrite has actually moved a bit. They're pushed down, there we go. So I've got 1 amp drawn at the moment. So one of the things that is happening here is that this ferrite is actually moving around a little bit because it's sort of bedded onto some blue tack, and it's just kind of shifting around all on its own. But anyway, I think that we are very clear that we can get our 1 volt for 1 amp. So I continued to play around with this for a little while, looking at the thermal drift and the amplification and how much effect the ferrite position had, all that sort of stuff. And I decided to call it a day there because, you know, without the ferrite core that I'm actually going to use, which is on order at the moment, and without the true size trimmers and all that sort of stuff, and the surface mount, etc., etc., and the thermal relief from the board, without all that sort of stuff, it's a bit hard to judge. And of course, This sensor is half as sensitive as the one that I'm going to be putting, so I've got twice as much amplification, that's twice as much thermal drift, and all that sort of stuff. So yeah, I decided I would make up the board anyway and see how it goes. If worse comes to worse, I can always strip off this section and just use them as general purpose amplifiers anyway. So nothing ventured, nothing gained, I suppose is the point there. I did make a few decisions about putting some limiting resistors around the trimmers and things like that, just to make them less sensitive, so it's easier to trim in the values you want. And I'll just show you that circuit diagram now. So here it is, and as I stated, just a few extra resistors, and the trimmers of course are actually much lower value than on the breadboard, so overall that should improve things quite a lot. And of course putting on a PCB and in an enclosure will also help quite a lot as well, but I'm still not convinced it's going to be enough. Now for part 2, I'm just waiting for the ferrites to arrive, then I can finish the design of the plastic enclosure and also the board. Those two are interdependent because I've got to position the sensor quite carefully, as you've seen. I'm expecting about a 3-week turnaround on the manufacture. So once that's back, we'll do some actual further testing on both bandwidth and DC performance and thermal performance. So anyway, I hope you enjoyed this. Please give it a thumbs up if you did. Of course, go ahead, subscribe, leave comments, all that stuff, and I'll see you next time. Take care.